Zoom it. Okay, there we go. All right, so when you're looking at waves, you have a couple of things. I don't know if you remember, if you've ever looked at waves or not, but basically, I'm gonna write over here a little bit about waves. So waves look like this, right? And there are some terminologies that we need to know. So one point to another identical point in another wave, this is known as wavelength, and that is symbolized by lambda, which is a Greek letter. Okay, so that's the wavelength. The amount of times a wave passes, let's say this area right here, right, in a given amount of time, that is known as frequency. So every time that, however many one of these, right, passes that area in a given amount of time, and that would probably be second, right? That's known as a frequency. So it's wavelengths per second, okay? So if the wavelength is very big like this, it wouldn't even be hardly any, right? But if it's little bitty like this, right, then there'd be a lot of them passing through. Okay, so that's wavelength and frequency. And then there's one more. If you think about it, this one feels like it's really lazy, right? Like lazy moving, just slowly. But it doesn't move slowly, by the way. It just looks like it moves slowly because the wavelengths are so big, but the speed is the same. That's the one thing that never changes. But this, though, the frequency and the energy are very related, because if you think about it, this one feels very energetic, like really fast. Yeah, and it is. And so the wavelengths, the longer the wavelengths, the lower the energy, right? And the higher the frequency, no, the lower the frequency also. So energy and frequency go together. Wavelength is opposite. Got it? Okay. All right. So
Yeah, so basically, if the waves are open, it's low energy, and if they're closer together, it's high energy.
and it looks like it doesn't it?
Yeah.
I mean, that's
Mm-hmm.
the thing that I like about it. Is when you look at it, it's like, oh yeah, that makes sense because it just looks just like that. Oh, she was already in here. Okay. Anyway, so yeah, that's exactly what I'm talking about. So see, now we can categorize them, right? We can stick them in there. Okay, so this one right here is the longest wavelength, obviously, right?
Mm-hmm.
This one right here is the shortest wavelength. So that means that this one's the highest energy also, and this one's the
Correct. The
lowest.
lowest.
And this
Okay.
is also the highest frequency and the lowest frequency. See, it makes sense. Oops, come here, you.
Yep.
See, it makes sense, and it looks like it too. That's the thing. Once you know what frequency and wavelengths are, it just makes sense. All right, so let's go to the next one. And I'm only doing waves right now. Okay, so electromagnetic spectrum. Normally, the way that I have it organized is not like this. I go from high to low to high, but it's okay because of the middle area, which is known as visible. So radio waves are the least energy because they're really long waves. Then after that, you would have microwaves. And then, come on, stay there. Then you would have visible light. Yeah, I don't see. Oh, no, wait. Nope, not yet. No. Okay, so infrared means below red. So that means that is longer than red. So that then there's visible, okay? Visible is the only thing we as humans can see. Ultraviolet means above violet, right? Then you have X-rays, which you can see your bones through. And then gamma rays, which is radiation that penetrates you, kind of like, I don't know if the Hulk, that was what made him that, is because he got radiation poisoned. So that's the gamma rays. And the gamma rays are the shortest wavelength, highest energy, and they're very penetrating. Whereas radio waves are really long and they don't penetrate anything. So that's kind of how that works, okay? Now, We're going to go to the next one. Well, you can check it if you want, but I know it's right. It's just one of those things. And with this one, we're going to open our book on purpose. Okay, so next. All right, so here are the equations. You need to write these down because we'll be using them again. So C equal nu, and that's that little, looks like a V times lambda. And that is actually the Greek letter nu, which is what frequency is, by the way. And then you have E is equal to H, which is a constant, Planck's constant, times nu. And then E can also be equal to, depending on what you get, H times C divided by lambda. And C, by the way, is the speed of light, which is a constant also. Okay, so let's put these in perspective. So a constant, the speed of light would be meters per second. So everyone that is there is meters per second, see? Frequency is hertz, and it is seconds to the -1 because it's over seconds. Remember we said it's how fast it travels in a second, so it's per second. But it doesn't have a unit on top, so it's just per second, or also known as hertz. And then we have Planck's constant, which is joules second, which is joules times second, not per second, but times second. And then we have energy, which is in joules. And then the last one that we haven't put on here yet, oops, I put lambda, oops, sorry, wrong one. The one that we haven't put on here yet is our wavelength, which normally we get it in nanometers, so we will have to convert it to meters, but it needs to be in meters in order for this equation to work, right? Because we got meters per second, so we cannot have nanometers here. So you need to have it in meters. All right, next. Oh, we could have checked it, but I didn't. That's okay. Okay, so this is energy, like I was telling you. Sorry, not you, you. And then this one is energy. This is not mass. Planck's constant is H. I'm just trying to find them all. Wavelength, there you are. That one is this one. It's not in every one. Frequency, there you are. Frequency. And then frequency over here. And then the last one, oh, I put you in the wrong one. Okay, and then the last one is speed of light. Okay, and now we can check. Oh, but we have one more that we don't have on there. Speed of light would have given us a wrong answer. Okay, so check it, and I know it's correct. So there you are. So you might want to take a picture of this or write it down with all of the names on them, because that is an important thing to know. Because when you are using these equations, you're going to have to know what they mean, right? In order to to substitute them. All right, so let's go to the next one. And the units are important too, because the units kind of give you a thought about what to do. Okay, now, this one is an interesting thing. If you look for in the book, you got to go to the book. It's just nothing else you can do, because you cannot memorize, at least I can't. I cannot memorize these. Notice it said ultraviolet absorption, right? Okay, so we're going to go to, where are you? See this thing and go to 7. And we're going to look at, where are you, 7? No, that's not what I want. Oh, sorry, this is where I want to go. There we go. Sorry, I went to the wrong one. I meant to go here, 7, 7. No, it is right. That is the one I went to. Why is it not giving me chapters? Because we're in chapter 1, that's why. Okay, let's just make it smaller. Make 7 smaller a little bit. Okay, these tools are getting in my way. Hold on. There we go. Let's make it smaller so that we can find 7. There we go. There's 7. Okay, so here, see, we already did the structure of the atom, right? But we haven't done this part. And I left it for last because it's a little interesting. Okay, so atomic spectra is what we want. And there it is. Okay, so over here, it's going to tell you somewhere in here. Hold on, I gotta find it. It tells you when it's a radio. Okay, there it is. Our eyes can only detect blah, blah, blah. Okay, hold on. Emissions. Emissions and absorptions is what we want. Okay. And this is something that I don't know if you guys remember from even elementary school, Roy G. Biv, which is the rainbow, right? Except here they've got it backwards. Let's see here. There it is, Roy G. Biv. See, ROYGBIV. See, that's the electromagnetic spectrum, and they're telling you exactly. See it? And there's the acronym.
Yeah.
You remember that, the acronym? Yeah, that's just to remember the order, and it's important. And remember that red is the widest one, you know, so this is the one with the highest wavelength, and violet is the one with the lowest. So when you write it down, you're writing it from low to high, okay? You should remember that because wavelength, I'm talking about wavelength, not energy. Energy is backwards, but let's see. Okay, so let me keep going to where I was going. I'm still finding that stupid thing because it's hard to find. And it is a little, oh, let's see. See, this is just the problems, and I like the problems, but that's not it. We're going to get to the problems. Here it goes. All right, this is a spectrum. Okay, so white light, blah, 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 blah. Nope, it's not saying anything that I want. It says, okay, when an element is heated or given an electric charge, the energy absorbed can be transformed into light energy. Okay, so when it gets excited, it goes up a level. Remember how we done SPDE, you know, all that. Okay, so it goes up a level. And then in order to go back to it, it throws off what is known as a photon, and it goes back down. Now, depending on the photon that it throws, and which energy range, right? It's that's what it's talking about. This is how we know. And then it says section 2. Okay, so we need to go to section 2. That's the problem, is we're not there. So we need to go one more. That's why I can't find it. Okay, here we go. And this part is just a lot of talking. Here we go. This is what we need. Okay, so you notice that it says, in the Bohr model of the hydrogen atom, the nucleus is at the center of the atom, and the electron is located in the circular orbits N through 6. See, that's what I was telling you. There's more to those that we learned than that. But depending on, and there it is right there. This is where you want to go. A transition, it says, to the N2 orbit produces an emission of visible light. The possible transitions to lines in the hydrogen spectrum, N6 to N2 is violet, N5 to N2 is blue, N4 to N2 is green, and N3 to N2 is red. You see that? Okay, so down here, it gives you all of those. Okay, so it gives you the colors. You see that? So an electron traveling from 6 to 1 is going to be a violet. You see that? Or anything beyond that, sorry, it's going to be ultraviolet. And infrared is going to be anything before that. So, but you notice it's going from to 2. So to 1 on the other one, right? From high to low, that's an emission. Now, absorption is different. It absorbs it and it goes up. So these are all emissions. All right, so that's what we want to look for. See how it does tell you right here. So The possible transitions are right here. That's in hydrogen now. So we're gonna go look at the, oops, yeah, at those. So anything that went to 2 that emitted, right? So we would say high to low. This is 1, right? Wouldn't you say that was 1? Let's see. This one maybe. And this is where I always get it confused the first time, but it's okay. You can get it confused the first time as long as you get it right the next time. It's good. Okay, so if it's going from 2 to 5, that's an absorption. And I think that's how it is. So I'm going to say that's correct. 2 to 3 is an absorption. And that's it. Anything with 2 there. Let's check. I might have it all wrong, but I think it's right. Nope, they're all wrong. Okay, so I got it backwards. See, like I said, you just gotta redo it, you know, and until you understand what it's telling you, you'll get it. So absorption just means it's going higher. So no, absorption, it means it's going to, and all of these are wrong too.
I think I got it. The absorption is the N equals 2
Oh,
to
and
the
I said
N equal
2.
3.
Oh, I put 2 and it was 1, wasn't it?
It's 2 to 3 and then 2 to 5 for absorption.
2 to 3 and 2 to 5?
Oh, wait. That's visible. Wait a minute.
Yeah, exactly. I think it's 1. That's where I screwed up. Because ultraviolet.
Yeah, it's 1. It's 1 to 2 and 1 to 5.
So
And then,
absorptions is this one because it's going up, right? Remember, anything
yeah,
that's going up. And is it 2, 5? From 1
it's
to
6
5.
to 1 and
And
then
then
9,
this
3 to
one.
1.
And then that one, right? Yeah, those, right? Like that. That's where I screwed up.
Yes.
I was thinking it was 2 and it's 1. I hope these are right. Please be right.
It is.
Yes, there we go. Okay. So see, it takes a little time even for me because I was reading it and I forgot that it was the 1, not the 2. Because I don't have it in front of me. That's the problem with the book, because I wish I had 2 screens. Okay, now you want to do visible or visible emissions. Okay. So visible is
It's
to 2, right?
2 to 3. Yeah.
So
And 2 to
absorption.
5.
Absorption is going up. Yeah, but I'm just explaining right now. And 2 to 5. And then the other ones is 2 all the way down to 2, right?
Yes.
So 6 and 4 and 1. And this one? No, this one's not. This one's an absorption, actually. But it's not that kind of absorption. No, this is an emission. Nope, that's an absorption because it's low to high. Okay, so that's it. That's all of them. Should be. Yeah, see, it's not as hard as it looks once you look at that diagram, right? And now you have infrared. Now this is where you got to go read again because I don't remember. Okay, so infrared was okay. 1 ultraviolet and 3.
It's 3.
3 is infrared. Yeah, see, you got to go read, right? It's how it works. It's just the only way to do it. All right, so 3 to 3. This one is an emission. That's an absorption because it's going 2 to 3, or should be 3 to something else. This is where I always get mixed up. It's 3 to something else, right? It has to absorb from 3. 3 to 1. No, 3 to 1 is an emission because it's lowered. 3 to 4, that's an absorption. Is that all of them?
I got 6
Oh, see, this
to
one's backwards.
3 and 9 to 4 for infrared emission.
I'm sorry, 6. I'm 6 to 3. Yeah, I know. I told you I get them. I always do this. I'm the one that screws it up. I need N3. Yeah, this one's 1, and that's all of them, right? But this is an
Well, I got I got 3 to 5 and 3 to 4 for the absorption.
3, 3, 2. I thought it, well, an emission, 3 to 5 and 3 to 4. Yeah, that's what I have.
Okay, and then 4 to 3 and 6 to 3.
Yep.
Okay, yeah.
That's what it is. You always have to have the one that you're going to on the end and the one you're coming from when you're absorbing. Yeah, that's how it works. Okay, so there you go. That's how you do those. They're not that hard. You just gotta read and then come back. All right, next. All right, so now you've got them, you know how to do this. So I'm not gonna even go there. But basically it's the same thing. Was it 1, 2, and 3, right? It was 1, 2, and 3, and that.
Yeah, you just gotta go back and look at the ones. That's what I did. I went back
Oops,
and looked
I
at
didn't
those.
mean to check my work because I didn't answer. Sorry. Okay, so now this is quantum numbers. Okay, remember I told you that you would have to answer a quantum number question? Okay, and this is misspelled. Oh my God, principal. It's principal with an A. Oh my God. Okay, so principal quantum number just gives you the n. Okay, so the n, that is the orbital shape, I guess. No, that's not the shape. What is this? Positive. It's just going to be positive integers of 1 through 7, right? Because it's your period. All right, so what does the period tell you? It gives you the level. So that would be orbital energy, right? That's what it would give you because it's the level. All right, the next one, which is known as the, see, I used to know it as a model, but I think it's called angular momentum now. And that gives you the shape of the orbital. And it is anywhere from 0 to n minus 1. And then the orbital orientation, that is what is known as the magnetic. And that is m sub L. There it is. And the numbers are L positive to L, that one. I know. And then the last one is known as the spin quantum number. This is the one that I was telling you about. And that one's m sub s. And the orientation is plus or negative 1/2. Where are you? Oh, there's on there. Okay, so that's just the direction of the spin. There you go. That should be correct. You might want to take a picture of that so you don't have to fill it out yourself, because that, I don't think that you should really be. Just knowing them is good enough. See? Okay. See, I used to know this one right here as a model. And that was where it was throwing me off. Remember, I said I have to go check it and see which one of these it turned into, because I remembered one and not the other, but it was good. All right, so next. Okay, this one you can do, right? All you got to do is look at the periodic table and start with 1s. And then it goes to 2s, right? And then it's 2p. And then it's 3s. And you know there's some distractors here because they don't exist. Then it's 3p. Then it's 4s. Then it's 3d. Then it would be 4p. Where are you? There you are. Okay. And then it would be 5s. And then the last one here would be in the, oh man, where are you? Let's see, did I skip one? 1s, 2s, 2p, 3s, 3p, 4s, 3, no, 4p, 5s. Next one would be F, but it's not on here. They screwed up. No, there we go, 4D. No, they didn't screw up, never mind. I got it. It's 6 and 7, that is D's, so no. All right, so that should be it. Check your work. And it should be good. All right, so next, then you have the partial orbital. Okay, this one is easy. All you have to do is do your shortcut configuration for each one of these, and then just use the outer part. So cobalt, let me get a periodic table. Where is it? I had it right in front of me. I probably put it underneath. Yeah, there it is. Okay, so periodic table tells me cobalt is argon, right? And it's going to be 4s2 in 3D 1, 2, 3, 4, 5, 6, 7. So 3D7. So that means each one of these, the first two are going to be full, right? Because it's 5 of them. And then the next ones are going to be separate. So that makes it 5 and 2 more is 7, right? Like that. And it says do not leave anything empty. So the other one needs to say empty, okay? All right, like that. Copper is an exception, remember? So we need to remember that. And it's going to be 4s1 and 3d10. So all of these are going to be full. Every one of these, full, full, full. And the next one's empty, empty, empty. Okay, and then the next one, selenium, he is 4p4. So everything's full until 4p4. So just drag all the full ones into it. And there's nothing empty on this one. Okay, so 4p4 distributing into 3, it's going to be, one's going to be doubled, right? And the other ones are going to be single. So that's 2, 3, and 4. Okay, and that's how it would work. And don't forget those exceptions, copper and chromium, because you may get chromium. All right, and that should be correct. Yeah. All right, so go next. All right, the full configurations, these are easy. You just drag in the 2s, the 3s, you know, whatever. All right, we're not doing that one. I'm just trying to do the ones that are more complicated. Yeah, that's not. Okay, this is a pool of 1. Okay, so how do you know how many unpaired electrons you have? Again, what do? You do exactly what we just did. All right, so chlorine is a P5. And this is all I need to know. Do I want to know the 4s2? Not really. I just want the P5 because everything else is full. So what I want to do is I want to take my P, right? 1, 2, 3, 4, and put my 5 in. 1. You see that? So 1 unpaired electron. Selenium. Selenium, we just did it. It was a P4. So all you would have to do would be to erase one of these, right? And look, it's 2, right? Cesium is at the beginning and it's an S6. I mean 6s1. Sorry, S6, 6s1. And it goes like, like this, right? So just 1, obviously. There's nothing beyond that. So this is what they want you to do, is just kind of think about what you know and just put it in there. Phosphorus. Okay, phosphorus is a P5, right? I mean, P3, excuse me. It's a 5, so it's in a P3. And you just need to put your 5s. Oops, come here. Okay, so 1, 2, 3, and it'd be 1, 2, 3. So it's 3 unpaired electrons. See? And then just, and that should be correct. All right, so let's keep going. And I don't know where my stuff went. Okay, this one, you just identify who it is. That's easy to do just based on the last of it. Remember how I showed you to do that? Okay, so if you go to 2p2, that would be 2p2 would be carbon, right? See, I can do it really fast because all I do is look at the ending. And this one, check always, when you have these, always check the S's just in case there's only one there. But it says 3D5. So that would be 1, 2, 3, 4, 5, officially manganese, right? And there you go. That's how you do it really quick. Let me clear all these drawings, which are annoying. All right, so check it, and that should be correct. All right, go next. All right, same thing. You would identify this one, 2p2, so again, carbon, right? Okay, so go next. This one, okay. Okay, it's 4s2, so that is calcium. It's telling you it's calcium. What? That's weird. That's so weird. Okay. Okay. Now this one's going to be interesting because you got to identify what periodic table they're asking you. So all you got to look at is, you don't even look at this, just look at NP5. So anything that's P5 is going to be 1, 2, 3, 4, 5. It's going to be this guy. You see that? That's all they want. That's all they want, is for you to know which one is row 5 of the piece, basically. All right. And you just say, check my work, then done. Okay, and then next. Okay, this one, it says S2, always check S2, and then it says D3, so D3 is this guy right here. Check work, that should be correct. Okay, next. Okay, we haven't done ions, but basically what you're gonna do is you're gonna do your normal cobalt, which is D1, 2, 3, 4, 5, 6, 7. Okay, so it's D7, right? So you're gonna have for cobalt, you're gonna have 7 in the D's. Oops. Okay, there we go. So we're gonna have 1, 2, 3, 4, 5, 6, and 7, and you're gonna have a 4s, right? Okay, I'm just doing them real quick. All right. So if you're gonna lose 3, chances are you're gonna lose these 3. Yes? Or do you think you're gonna lose this one first, then this one, and then this one? Which one do you think? Because that matters. Or are you going to lose the S's first, since they're lower energy? I don't know. You tell me. Which one do you think it's going to happen?
Wouldn't it be the ones that are not paired?
You would think, but then you leave paired, and that's against Hund's law, Hund's rule. Remember that? So if cobalt, yeah, I know it's kind of tricky. So if cobalt looks like this, right? And this is your normal cobalt right here. Right, so this would all be empty right there, right? This is what cobalt looks like. Now, cobalt 3 plus, chances are you're going to lose one of the D's. So this one's going to be gone. You should say empty here. And do you think these or these? Well, they were filled in order of energy, right? So which one do you think is easier to lose? The one that has higher energy or the one that has lower energy?
Lower.
So then it'd be these two, wouldn't it? According to what we know. And that should be empty like that. All right. Copper was like this. And you notice they just want 2. So copper is usually like this, yes, because it's one of those exceptions. Okay. So copper is going to lose electrons. Chances are it's going to lose one of these for sure, right? And that's going to be 1. And then the other one's going to be this guy. And that's going to be empty. Make sense? Selenium's easy because it's piece, and they just lose the piece. Gain the piece, sorry. I said lose. I mean gain. So basically, you're going to have selenium is going to look like this, right? I wish I could make them in different color, but selenium, let's see, it's P, where are you? P4, okay. So all of these are going to be full for selenium, right? And then you're going to have 4 on the end. And so this one makes sense a lot. See, because you can kind of see where you're going to put them, don't you? And if you said you would put them here, you would be correct. So then you would need to fill those out. So you need to take these out like we did. Say I just take them out. Okay. And instead of putting that one, I need to put these. So that's what I would guess. This is what I would guess would be working correctly. Did you try it?
Yeah, but I must have missed this lecture because I'm lost on this question.
Okay, so basically what's going on, okay, see how it didn't like this? Okay, why didn't like that? Because we said that it might go easier with the lower energy. Okay, so he says it's not empty here. Why do you think this happens? Why do you think this is not the right answer? The empty is good. See, everybody else is good, but this one he didn't like. Why? Because it doesn't
Because
like
that one needs to have just the arrow up instead of arrow down, instead of both arrows.
it needs to have, yeah, it can't have an empty. See, I put
Right.
empty, but I did that on purpose because you would think it would be empty, right? But it can't be empty. Not if you have this many, you're breaking Hund's rule. So you need to move one over. Right, exactly. See, you do understand it. When you lose electrons, you have to know that this is going to be turning into 2 of these. Yeah.
Oh, okay. It breaks it down. I get you.
Does that make sense now?
But when do you know to break it down?
Because Hund's rule tells you that you cannot have an empty orbital if you have more than, you can have an empty orbital if you run out of electrons, but if you have the number, you have to move them over.
Okay.
Okay, so that should be correct now. See? Because we didn't break Hund's rule. And yes, it was correct when you answered that, yes, you would want to take the lowest energy first, which it did, right? It took the two, in both cases right here, it took the S's, right? But you notice we didn't leave anything empty on this side. Whereas here we did. And if we put an empty there, that's a wrong answer. It needs to move one of the doubles into a single. So that makes more sense. All right, so now you know how to make ions. It's really, remember, plus means they lost, right? And negative means they gain. So obviously they're going to gain where there's a hole. There's no doubt on that one. But the losing, you have to think about. Okay, so when they lose electrons, when they lose electrons, you have that to think about. Okay, so and this was just one pool. I think that was it, but I don't know if that's all of them. We might get another one. Okay, now this one, remember how I keep always telling you they're isoelectric? All you have to do is look at the number that you have. Okay, so if you have sulfur has 16, but you added 2, that's going to be 18, and that's going to be argon. See that? Oxygen, you had 8, and you added 2, that's going to be like neon. These are easier. The negatives are easier. So let's just do those first. Chlorine, you had 17, and you added 1. That's going to look like argon again, right? Iodine, you had 53, you added 1, that's going to look like xenon, and it's not here, so let's leave him alone. Any more negatives? Negative, yeah, here we go. Hydrogen had 1, you added 1, looks like helium now. Is there a krypton in the house? Not on these, there isn't. Okay, so now let's look at the negative ones. Okay, the positive ones, I mean. If you take one away from cesium, it's going to look like xenon, so that's not one. Oh, arsenic, there we go. I knew there was one. Arsenic, we had 33, we added 3. It looks now like krypton because it has 36. There you go. Those are the negatives. The negatives are easier. All right. Cesium didn't work. Beryllium, okay, so beryllium, you had 4, you took 2 off, it looks like helium. Calcium, you had 20, you took 2 off, it looks like who? Argon, right? Because strontium, you had, where are you?
You accidentally put it in the wrong box.
I put it in the what box?
You put it in helium.
Oh my gosh. Sorry, thank you. I was trying to go for my next one, and I guess I didn't carry it all the way down. Okay, so strontium, you have 38. You take 2 off, it goes to krypton, doesn't it? Iron, see, these don't match as well. You saw why, right? Okay, so cesium we did. Lithium, you had 3. You took 1 off, it goes to helium, yes? Aluminum, you had 3. 13, sorry, you took 3 off, you are going to neon. Magnesium, same thing, neon, because it had 12. All right, so what about the rest? Okay, iron. Iron would go to krypton, but it doesn't have, I mean, I'm sorry, to argon, but argon doesn't have D, so it can't be it. You see that? Right? Does that make sense? Because argon,
It doesn't have what?
any D electrons. Iron does. Iron is, let's see, iron is actually argon. So the noble configuration for argon is, for iron is argon. And then it would be 4s2, 3d, 1, 2, 3, 4, 5, 6. Okay, so 4s2, 3d6. Remember how we did that? Okay, so whatever we take off, we're still going to have these. Does argon have those? I mean, those, yeah, it doesn't, right? Because it's on the level 3 where there are no Ds. You see that? So it will never be equal, in other words. No matter what we do to this, because all we're taking off is 2 electrons, right? So it would actually be 6, right? No, let's see, 1 more. Sorry. Yeah, there we go. I was counting them and then I forgot that I needed to. Okay, so there, that's what you have in this. Okay, so if we took these 2, we still have all of that. That argon does not, that argon does not have. So no, it will never be equal. Make sense? Because argon would be 3d2. I mean, not 3d, sorry, 3s2, 3p6. There is nothing equal there. So no, let's clear it. It would have to lose all of the other electrons to look like argon. As a matter of fact, it would have to lose all of that, right? To look like argon. Okay, so let's clear it. And that should be correct. Let's check. It should all be correct. Unless I put it in the wrong place while I wasn't looking. No, there we go. Because iodine didn't match any of these because it was xenon, remember? So that's why we didn't put them in. But iron definitely can't be in there. Okay. Okay, now this is the organization by atomic radius, okay? Remember I told you you would have to do this at some point? And the point right here is looking at, remember, the atomic radius increases going this way and down, right? Okay, so we need to, for the largest, is going to be the one that's farthest over to the left and farthest down. So who is that? I would say it's rubidium or strontium. Rubidium. It's rubidium. Rubidium would be the largest, right? Then strontium. Then it would be calcium. And across, I think it's arsenic. And some of these are going to be wrong, and that's okay. We're looking at the trend. And it's okay if they're wrong. Okay, then arsenic. What do we have next? Argon and chlorine. Argon is going to be smaller than chlorine. Yeah, okay, so chlorine is next. According to this, it would be like this. Now, remember I told you, this is a trend. We have them organized like we think they're going to be. And if there aren't a couple of them aren't right, and there's a reason for that, then you need to reorganize them. Okay, so which one goes first? All right, see, the smallest should have been P. Why P? No, never mind. Nope. That's me. I did this wrong. Return to question. Yeah, I did this wrong. P, then Cl. I didn't see P. And then AR. AR is the smallest. There's no doubt. Why is AR the smallest? Because it's farthest to the what? Left. Right. Sorry. Check it now. Now it's correct. See? That was me. Sorry. Okay, so next one, increasing atomic radius. Okay, so this one, and I'm going to make it a different color so you remember that there are some that are one way and some that are another way. So we're going to make it red this time. And this time is this way and up. Remember? Okay. So for this one, and one of the things we know is that the more they lose, the smaller they get, right? So we know that potassium is going to be the smallest of all, then calcium. And also, if you look at it, calcium started off, no. Calcium is going to be the smallest of all, then potassium. Calcium started off as smaller anyway, and it got smaller. And potassium started off a little bigger than calcium, and it got smaller also. Now, these guys get bigger. Which one of these gets biggest? Okay, well, according to what we know, phosphorus was already bigger to begin with. Yes? So it got larger, but it started off larger. And then this S2, see, notice it just says P2, right? So P2 negative is going to be in the middle, and then this one's going to be there because this one would have been the smallest of the negative ones. All right. So that should be correct. Let's see. Yeah. Okay. So next. Okay. So this one, you just put in which one's smaller or larger. None of them are ever going to be equal. So unless they're the same atom. So we remember that calcium, the only ones that I really want to do is that negative ions get bigger, right? And positive ions get smaller. All right. And here, who started off as bigger on sodium and magnesium? And also, who lost more? That's the other thing. When something loses more, they get smaller. So now, N3 and O2. Well, O is bigger. No, O is smaller than N. So I would say that N is bigger. Argon or neon, there's no doubt on that one because argon's on top and neon's, I mean, on bottom and neon's on top. So that means argon is bigger because it's got one more layer. And then aluminum or phosphorus. Okay, so here's where you remember what we talked about. Aluminum, when it loses, it gets 10, right? And 10 looks like neon. So that's what we're going to write underneath it. We're going to write the word neon. And phosphorus has 15. When it gains 3, it looks like argon. Which one of these is largest? Exactly. See? That makes it easy to do. That's when you have to remember your little things. Okay, so oxygen or sulfur, might as well do all of them. Lithium or nitrogen. Well, lithium is farthest over to the right, correct? So this is atomic radius. So lithium is going to be larger. I'm sorry, I said right, I meant left. And then oxygen or sulfur. Oxygen is above sulfur, so sulfur is going to be bigger. And that's what I would know, what I would do. Now let's see if it's correct. Should be correct. Yep. Okay, next. Let's clear all this stuff. Well, maybe not all of it, because we're going to need that. Okay, so if you were to organize this by increasing atomic radius, how would you do it? Notice it says increasing. Who would be first? Who would be the smallest out of these? Anybody? No?
It would be NE.
Yes, neon. Makes sense because it's the farthest to the right, correct? Then who else?
Nitrogen.
Nitrogen, okay. Then
Life.
B.
boron,
And it.
Sodium,
Lithium.
and lithium last. Why is it the
I
largest?
thought it was lithium first, then sodium.
I know, but somebody said that. So I just put it where they told me. So, okay, if you think sodium, look at where sodium is in relationship to lithium and look at this trend. See how you would switch it? Because
Yep.
lithium needs to be, yes, exactly. Do you see why it needs to be on the bottom?
Right.
Because it increases going down. So that means the largest is going to be sodium. All right.
Right.
Perfect. Okay. So check the work. Should be correct. Yeah. By trends, it's usually pretty good. Okay. I'm not going to keep doing these, but you know, you get the gist of it. Okay. So we're going to keep going. Okay. Okay, so this is just what I did here, these arrows. All right, so atomic size is this one, right? So that would be, oh, look, and I even drew in the right color. Okay, we know that all the other ones are backwards, right? So it's this one, right? The green one. Up and to, yep, that would be that one. Electron affinity, that goes there. And metallic behavior. So if you think about it, the most metallic element is francium. Therefore, everything increases to the left and down, right? So it's this blue one. And oxide basicity. Okay, so this one's a little interesting. Remember electronegativity? Okay, so if it's more electronegative, it makes less basic. Okay, so least electronegative, more basic, it also includes this guy. Because electronegativity is this trend in the red over here that I drew. Okay, so if you're looking at basicity, it's going to be exactly the opposite. So it's going to go with the blue trend. All right, and then let's see, check the work. It should be correct. Yep. All right, next. And that always is good to know. Okay, this is the same thing. We're just going to skip that one. Skip that one too. We don't need to do all of these together. Okay, this is something you need to read. Same here and same here. All right, group 3A. Okay, same here. This is another one. Okay, now this one, I'm only doing this one with you because you might not understand what it's telling you, but basically it's telling you an alkali metal and a halogen. So who's an alkali metal? Sodium. Who's a halogen? Chlorine. So there you go. Is there another one? Potassium? Yep, potassium's one and bromine's one too. Right, so there you go. That's it. That's the only ones. That's how you know. It's just what they're telling you to look for. And you notice the next one is going to be, okay, so alkaline earth metal and a carbonate or a sulfate. Okay, so alkaline earth metals is calcium, and that's a carbonate. Iron is not an alkaline earth. So barium is, right? Barium is an alkaline, and that's a sulfate, SO4, see? And that's all they're asking you to do, so. Those are easy. And that's all of the questions on this one. All right, so now let's go back. I'm just going to save and exit and just get out of there. And let's go to the problems. This is where we need to look at. Okay, so let me go back to home. There's only 5 problems in the next set, okay? And they're going to be applying those ones that I showed you. And then after that, you're ready for your test. So that's what I was telling you. Once you're ready, that's it. Okay, so we are going to look at these problems. And we have those formulas, so you got to remember them. The 3 formulas that we looked at earlier. Okay, so this is the main thing that you want to look at. You want to look at what they're asking and what they're giving you. Okay, you notice it says frequency. They want frequency. And then they're giving you wavelength. So which one of our formulas have frequency and wavelength? Well, the only one was the one with C, right? And remember that triangle that I always have you draw? Okay, so if C is equal nu times lambda, right? C is the speed of light. Then to get frequency, it's just going to be C over lambda. Okay, so C, which is the speed of light, which is, by the way, 3.00 times 10 to the 8th meters per second, divided by, notice they gave it to us in nanometers. So here's where I do my trick. I don't even bother changing it because we're just going to do division and multiplication anyway. I mean, division and then addition of the other part, which is the wave. I mean, not the wavelength. I'm sorry, I'm reading wavelength at this point and I'm saying the wrong thing. Okay, so that is in nanometers. So what conversion factor do we need to put in front of it to make it meters? That would be times 10 to the negative 9, right? Because we're going from low to high. Meters. All right, now we can actually cancel those, and it's 1 over S, which is frequency. All right, so if we divide, now, if you have a calculator that does this, you can just enter it by putting EE. But if you don't, this is where I want you to do 3.00 divided by 48.4 and get that number. And the number that you get is 0. In my case, okay, and we have 3 sig figs, so we got to stick to that. So it's 620 according to mine because, oh, there's another 0, sorry. There we go. According to mine, because there's a 9, 1 9, and then an 8 afterwards. So we need 3 sig figs. We do it like this. All right. Now, that's times 10 to the what? Okay, so it's 8 plus 9, right? But then we got,
I hate doing CPs. I thought we was done.
1, 2. So we increase, we decrease. So you see, look what I did. I did all of it in one. I know, because you already know how to do it. So 8 plus 9 minus 2, right? So
Yes.
the answer is going to be 6.20 times 10 to the 15th, right? All right, so let's
Oh,
put,
yeah.
yeah? Oh,
Yes, ma'am.
okay, I'm just saying, I'm just, you know, I did all of it at once, so that's why I was trying to show you 6.20 and then times 10 to the 5th. Oh, that's a comma. Nope. 10 to the 15th. Okay, now what kind of radiation is this? Remember I told you we need to leave it open for that? So we need to go back to the electromagnetic spectrum thing. Okay, let's see. I think it's in page before that, somewhere in here. Yeah, there it is, right there. You see it? Okay, so it's to the 15th. And we are looking at frequency. It's ultraviolet. You see that?
Yeah.
Okay, so there's what we say. All right, so the type of radiation it is ultraviolet, and that should be correct. See? Pretty good, huh?
Yeah, when we know what to do.
Well, but that's why I'm showing you. But do you see how everything that we've learned applied right here?
All work together, yes.
Exactly. Even the little triangle applied here. You know, everything. Yeah. And that's what you want to pay attention to. So you have conversions, you have, you know, the exponent thing, you know, all of that, working with exponential numbers. If you don't have a calculator, if you'd have had a calculator, it would have given you the answer anyway. But sometimes you don't. So, all right, so let's go to the next one. And let's clear all this junk first. Okay, so what is the next one? Okay, again, look what it's asking. It's asking for wavelength this time. And it's giving you what? Frequency. So it's the same thing again, right? Except backwards. So we have the same little triangle that we're using. Same thing except backwards. You know what I meant. Nu times lambda, right? So we're looking for this time, right? So it's c over lambda. So again, the speed of light, 3.00 meters per second. Oop, times 10 to, I can always forget times 10 to the 8th. Doesn't matter where I put it, I just putting it in. All right, and then the bottom is 8.28 times 10 to the 14th. 14th, oops, 14th, positive 14th. There we go. Seconds to the -1. So when you take it off, you see, you're going to get just meters, which is what you want. All right, so you're dividing 3 into 8.29, 3.00 into 8.28, sorry, not 9, 8. And that's going to give you, this is the number I got, 0.36. And how many? Yeah, we need 366. So 362 times 10 to the what? All right, so 8 minus 14. You see that? Because this one comes up as negative, remember? Okay, and then we also have increase 1, decrease it by 1. So it's really minus 15. So it's going to be -7, right? Am I right? Yeah, 15 minus 8 is 7. Yeah. Okay, so it is -7. Okay, so this is, the answer is right there. That's it. We don't have to calculate anything else. It's in meters. They want it in meters, so thank God. So we don't have to do that part. So the answer is, we put it in 3.62 times 10 to the -7. And it didn't ask us what radiation that is, so we're just checking it. See? So all of that I taught you before, it applies here. And it also, if you don't have a calculator, if you have a calculator, you can do it like that. Okay, clear all of that. And then go to the next one. All right, photon energy. Oh, now we have energy. We're going to use one of the energy questions. Now let's see what they're giving us. What is the photon energy of light with a wavelength of this? Okay, so we know we need the one with wavelength, which is the long one, the one that has 2 parts. Okay, so this equation, since they want wavelength, right? And notice it's in nanometers, so pay attention to that too, because wavelength is equal to, so in this case is E equals to HC over lambda, right? So we solve for that, we get HC, let's see. Oh, Lordy, let's see, what do we get? Yep, we get the wavelength. No, we need the energy, so that's it. We don't need to solve for anything. We got energy is what they're asking for. So energy is going to be equal to Planck's constant, and there it is. Look, they gave it to us. So 6.626 times 10 to the negative 34 joules times second. That's times second, not per second. Times, and I'm just going to put parentheses, the speed of light. So that is 3.00, and I always forget that exponent, not this time, 10 to the 8th meters per second. Okay, notice right here, these seconds are canceling already, and we have joules and meters. So the bottom, it's frequency, which is seconds, yes? I mean, sorry, not frequency. It's wavelength, which is meters. In this case, is nanometers. So we need to put 211 times 10 to the negative 9 meters. Don't forget that part, because meters cannot go with nanometers. All right, so we're going to get just joules, because meters is not going away too. So when we do all this math, which we need to, all right, so you can do the top in parentheses if you want, and it's 6.626, and then times 3.00 divided by 211. And this is with no, with no exponents yet. So we're going to do this like we learned. 0.0, and we need 2,942. Okay, times 10 to the what? Okay, so the top is going to be negative 34 in 8. So negative 34 plus 8 gives me 26, negative 26. And then plus 9, right? Because the bottom comes up as positive. So plus 9. So plus 9 again, that's negative 17. But then we got 1, 2 to increase and decrease by 2, right? So negative 19 is the actual answer. So minus 2 here, right? Gives us 9.42 times 10 to the, let's see, again, negative 17 plus 2 is negative 19, correct? Joule, and that would be meters. So the one sorry, not joule. It's joules, sorry, joules, not meters, joules. Meters cancels, that's what I was telling you. All right, and so it's joules. All right, so it's a very small amount of energy, but it is there. All right, so that sounds about right. Okay, so let's put it in. 9.42 negative 19. I know it was a big mess, but that's what ended up being, right? So it's really negative 28 plus 9, which gives you 19. Yeah. All right, so negative 19. And that should be correct. Check it and see. Where are you? Check. I think, oh, there it is. Check my work. Correct. See? I know that was a big mess, wasn't it? But it is math. I mean, it is the only other math that you'll have to. Okay, let's erase all of this. Oop. Okay, there we go. Now look what it's asking and tell me which one you would use. Which formula? Based on what it's asking you to find and what it's giving you. Anybody?
It's looking for the frequency.
Yes, but which formula would we use? It's looking for the energy, yeah, for the frequency from energy. You see that? Yes, it will be posted. Just, I'm sorry, I hadn't seen. It will be posted again. Okay, so what is the frequency? Okay, so you notice that there was a third equation we haven't used yet, which is E equals to Planck's constant times frequency. Okay, so if you do your little triangle, right, energy is equal to H times nu. Nu is what we want, so it's E over H. So E is, frequency is going to be equal to E, which is 4.429, sorry, times 10 to the 20. I know I speak what I'm looking at, and I'm sorry, I was looking at the 2. All right, joules, right? Divided by Planck's constant, which was 6.626. Remember that one? Times 10 to the negative 34 joules second. And joules cancels and you get frequency, you see? So that makes sense. All right, so all we got to do now is divide. All right, so it is 4.49 divided by 6.626. Oops, 626, okay. And that gives me this 0.6, and we have 3 sig figs, so 678. Yeah, 678 times 10 to the what? Okay, so the top is negative 25. The bottom is 34, so it comes up adding, right? And then we move 1 over. So we increase, we decrease. So there's really 26 minus 34. And that gives us negative 8. So there's your answer. It's 6.78 times 10 to the negative 8. And that would be what we need to put in here. 6.78 to the negative 8 hertz. Everything was meeting. Yeah, that's fine. Okay, so let's check it. And hopefully that's correct. Oh, something's wrong. Okay, what did I not do? No. What did I not do? Something I
It
didn't.
should be -9.
Oh, it's positive. It's positive. I don't know what I'm thinking. Yeah, it's positive 8. It's not negative 8. It's positive 8. Why? Because this is positive. You see that? So it's really 34 minus 26, which ends up being a positive. That's what the problem was. Okay. There you go. See? Because the pluses have it, right? This is much larger than negative 26. So, okay. So there you go. All right, clear all those drawings. And this is the last one. And this one I wanted you to see because I want you to see how to enter it. Okay. Oops, sorry. the check mark. All right, there you go. All right, so let's do this one. Okay. So first of all, we're going to write them down. Okay, so bismuth, what is its abbreviated configuration? So let's find out. Let's look for the, let me make it a little bit wider. Okay, so let's look for bismuth. Bismuth is over here. So look up and it's xenon, right? So we got xenon. So bismuth is element, what are you? 83. So if you go up one row and go all the way to the noble gases, you see xenon. So that's where it starts, xenon. And then after that is 6s2, 4F14, 5D10, and 6B12. Let's see. Where are you, Bismuth? I lost you. 1, 2, 3. 6B3, right? That's the configuration you're going to enter. Okay, so how do we do that? First of all, we click on the little square and we put exactly like what I wrote. All right, so we put the bracket, we put xenon, capital X, little e, and all of that has to be exactly like that. Now, 6S, you just put 6S and then click on this thing and bring it up. And then if you don't have a computer with arrows, you can use this one. Boom, see how it went down? But if you have an arrow computer, it'll work that way too. So 4F, again, go back up, 14, and this time I'm going to do it with my arrows. See, I can do it with my arrows or I can do it with these arrows right here. It doesn't matter. The next one is 5D. And again, go up, and that'll be 10. And then again, go back down, whichever method you want to use. And then 6P. And then go back up again, and 3. And then you can just hit enter from there. And that's correct. You see that? Exactly what I wrote here, right? And it looks like what I did. Okay, so that's what you want to make sure that it looks like that. Otherwise, it's going to be wrong. Okay, so I'm going to clear that. Next one that we're asking is radon. Okay, so radon is again going to look exactly like this, except it's going to be 6p6. So I can just copy from up there. Okay, so it's going to be xenon, because radon cannot be its own electron configuration, right? So it's 6s2, and again, go up, 2, bring it down, 4f, go up. You cannot, unfortunately, you cannot bring it up with the arrows. That I tried. And then 5D, go up, 10, bring it down, and 6P, go up, 6, and enter. And that's that one. And the last one's an easy one, is radium. And radium is radon. And 4s2. I mean, 7s2. Did I say 4s? Okay, radium is radon. So Rn. This is where I always screw up. I get these two backwards sometimes, and I put RA in the middle, and I'm doing RA, not RN. So it happens. And then 7s. And see, I tried to do it with this one. See, it doesn't work. You see that? So you got to actually use this guy and this guy right here, or it doesn't work. And then you can just enter, and that's it. And then you check your work, and they're all correct. But you have to enter them correctly. So that's the one I wanted you to see last. And that's all of it. And see, you have, if you did it along with me, you have just finished that one entire exercise assignment, right? All right. And I know you had different numbers, but the gist of it is what you were getting, right? All right. So that's all. Let me go and save and exit or submit or whatever. I don't know if I finished it or not. So I'm just going to say save and exit. All right. And then that's all of them. And like I told you, and this is for the people that came in later, you're still going to do one more reading assignment, but after that, all the reading assignments are turned off. I don't know if you can see, chapter 8 is turned off and you don't see it. Chapter 5 is turned off. Chapter 4 and 6 are turned off. So all of the rest are turned off. Okay? So you don't have to worry about them. And if you're ready to take the test, which you are, I'm going to go ahead and do it right now. And I'm going to grant you your 3 tries. Oh, I got to go to 7 though. I always do this. I forget to click on it. Okay. Assessment. Click on it. And I'm going to give you extension to everybody for 3, which is what I do for everybody anyway. Okay, so manage states. Oh, this is in my way. Come here, you. This is in my way now again. Okay, there we go. Manage states. It's weird, but oh, okay, this is in my way all the way. What on earth is this doing? See, it when I hit this thing up here, it's in my way. There we go. Manage dates. All right, so extensions, that's everybody. I just have to click everybody, even though they're probably half of them are not even here, but it's okay. I still do all of you. And you're ready to take your test now. Some people actually do this
Thank
online.
you. But I have a
I
question.
know you're not in this class. I know. So I'm going
Yeah.
to have to put you in for the 12:30 class.
I was trying to attend this myself.
What now?
I send you an email. I can't attend it.
You can't. I know you can't. Yeah,
Okay.
I know you can't because you're in the wrong class, but that's okay. All right, so that's everybody has an
Is this
extension.
class lecture?
Yeah, this is lecture. Mhm.
Okay. Can I leave now?
Yeah, you can leave. I was just
Thank you
showing
so
you
much.
that I'm extending it and you're ready to take that test.
I'll do it. Thank you.
All right. Yeah.
Have a nice day, man.
Okay. Bye. All right. So that's that. I will be posting this recording soon.